Hi, I'm Carolyn McCreary, and I have been a selectman in Ayer. I served 2 terms starting in 2006. But the reason I'm here today is because of my desire to help clean our planet from reduce our CO2 in both our atmosphere and in our water. And I'll tell you, I learned about global warming and climate change through the movie An Inconvenient Truth in the early 2000s. I decided that I needed to do my part to help us clean our planet. I did what our government had suggested. I engaged mass saves to help me insulate my home more securely, put solar panels on my roof, used a heat exchanger for both heating my water and air. And in fact, my electric bill kept rising. So it was clear to me that my solar panels were not allowing me to have much effect on my carbon footprint. In addition, I got an electric car. My electric bill rose. So I was becoming pretty discouraged about the idea of renewables as the solution to our climate problem. And as I was fretting about this, I saw this presentation by David Butts and was really encouraged to follow his lead and do more study into the realities of energy. I am very happy to introduce David Butts to you. His depth of knowledge of energy, of power production is immense. So please welcome David Butts.
Thank you, Carolyn, for that kind introduction. What we want to share with you today is what we call energy realities. In the paper-thin atmosphere of our precious home, our planet, we invent, develop technology, explore the frontiers, and advance medicine, but now pay a very high price for the electricity. The burning of fossil fuels results in an alarming excess of CO2 introduced into the atmosphere. This pollution threatens us with climate change, ocean acidification, which may be a much greater danger than even climate change, and unknown hazards. As a result of these threats, people who are concerned have often come to 2 conclusions that I highlight here today, namely that renewables are the answer to this problem, and second, that nuclear is something dangerous that we should eliminate. I want to dig a little deeper on each of these, into each of these assumptions, because there may be a little bit more than immediately meets the eye. Where do we go from here? Well, let's consider a logical starting point. If we are going to eliminate fossil fuels, the first thing we might say is all hands on deck. We need everything. And I highlight here the 2 things that we're going to consider, renewables and nuclear. Before we pick one and just throw the other out the window, we need to look closely at both the pros and cons of each of these. Please note that I put renewables in quotes. When we speak of renewables, throughout this presentation, we will be referring to wind and solar, but technically wind and solar are not renewables. They represent diffuse energy streams within the atmosphere. Renewable is something like a crop that you can plant and harvest again and again. Well, starting with renewables. Renewables are in fact green. They have many fine niche applications. Here you see irrigation coming to a third world farm for the first time. Tiny solar panels supplying a pump. Really life-changing for the people that are employing it. Wind has provided service for centuries, pumping water, grinding flour from grain, and bringing agriculture to dry land. Now, these 2 renewable sources are supplying energy to the grid, large-scale industrial applications from both solar and wind. But renewables have big problems. The first problem to highlight is material requirements. As you can see from this bar chart, solar photovoltaic and wind require enormous amounts of glass, concrete, steel, and other materials. You might notice on the fifth bar that nuclear is very low by comparison. We'll come back to that later. But these material requirements are enormous, and all of the front-end requirements for mining and processing are also to be considered. For an example, this is the preparation of a base for a large wind turbine. Notice that there's a deep excavation, then a concrete working pad skim, tons of rebar, tons of concrete yet to be poured in order to prevent this from happening. This is disposal of wind turbine blades after their relatively short lifetimes. Notice the size of the bulldozer. These blades are very difficult to handle. There are people trying to find ways to reprocess them, but that is not simple with these fiber-filled non-thermoplastic materials. Here you see what happened to the solar farm in Puerto Rico after Hurricane Maria came through in 2017. This is one small portion of that solar farm. Now, solar panels contain glass and silicon and heavy metals like cadmium and lead, and now shards of all that material scattered throughout this solar farm on the ground. Hurricanes will strike these solar farms again, of course, and we'll have the same situation arise again. But even for the majority of the solar farms that do not experience this fate, all of this material still has to be reprocessed in a relatively short period of time. As it happens, we don't really have any reprocessing methodology in place, and it's not very economical to do this reprocessing. So frequently this material ends up in third world waste dumps where children crawl all over it. It's also worth noting that if we followed the somewhat famous and now discredited roadmap for an all renewables future from wind, solar, and hydro, by the time it was all built out, we would have to replace over 1 million square meters of solar panels every day, forever. With renewables, we also have a big China problem. This could be done in a better way, but this is what happens when we are building solar panels in China, which is where we get most of our solar panels from. The Chinese father says it's poison air, you can't go outside. Hydrochloric acid, silicon tetrachloride in the soil, large amounts of coal burned to melt the polysilicon, and they have very little concern for the environment. An executive has said if it happened in the US, you'd be put in jail. Likewise, for wind. Our wind turbine generators require rare earth magnets, particularly neodymium. The Chinese monopolize the rare earth market worldwide, and this is what results from processing rare earth materials, this enormous sludge lake that goes on for miles. This may be surprising to hear, but compared solar panels to nuclear providing the same amount of energy, 300 times more waste by volume. This is not something to be ignored. In addition to materials, we have to consider the land implication of installing renewables at a very large scale. You notice the little green square down there. A power plant of any kind, coal, oil, nuclear, can be easily installed to supply a gigawatt of energy on a square mile or less. Whereas wind requires upwards of 400 and solar upwards of 75, depending on location and topography and all of the other things. The comparison is quite stark. Just as an exercise, this is not how we would actually do this. If we tried to power Massachusetts with all wind, we would have to cut down trees and occupy the blue land you see there, something between the light blue and the dark blue, in order to supply that power. With solar, it would be the yellow area. With nuclear, it would be just that small red dot, maybe 6 1-gigawatt plants. And that's before expanding electricity to support electric vehicles and heat pumps. Now, naturally, we wouldn't even try to do solar at that scale in Massachusetts. We're at a terrible latitude and we have snow in the winter. But this gives you an idea of why the plans today are to put that wind offshore. It would still be an enormous installation in salt water, subject to hurricanes. The land requirements have two aspects to them. One of them we just looked at. The weak diffuse energy flow means that we have to carpet the landscape in order to get any reasonable amount of power from these sources. But the second thing is irregular flow. This results in what we call low capacity factors. A capacity factor is the fraction of the maximum or nameplate capacity of a generator that you actually get out on average. Note that for solar it's 15 to 25%. So if you consider that number, if you wanted to install a gigawatt of solar capacity, you would have to install 4 gigawatts of solar generating capacity and be able to store everything that you generated, which is a whole nother problem. Wind is a little better. Land-based wind is around a third, and if you go offshore, it does get higher. The winds are better, and you can access higher winds that can be up in the 40%. Note that nuclear has a capacity factor above 90%, and it has been like that in this country for many, many years. That's way higher than even natural gas and coal. This is what happened in Germany when they installed a lot of wind and solar after the Fukushima accident. If you look at the top of the light blue, that red line, that's the installed capacity. But the blue spiky stuff is what you actually get out of that capacity because of all this irregularity and low capacity factor. Now, in order to actually supply the grid, you've got to fill in the remainder, the light blue area, and unpredictably. So what do you fill in that extra with? In Germany, it's coal. And in fact, now it's lignite coal, the dirtiest of coal. In France, where they get over 70% of their electricity from nuclear and combined with hydro, they get a very high supply from green sources. They, with Sweden, have the cleanest air in Europe, while Germany's air is getting dirtier. And France pays half of what the Germans pay for electricity. Now, this backup problem applies to us here in New England as well. So in Germany, we just mentioned it's coal. In New England, it's natural gas. But natural gas comes in by pipeline, and this means that you have to use it pretty much instantly. We have a little bit of LNG storage, but basically it's coming in on a momentary demand type basis. And in the winter, home heating gets priority. So there's actually the possibility, now revealed, that we could end up having natural gas backup to our electricity grid cut off, resulting in rolling blackouts. Personally, I've studied the supply side of this whole issue for years, and I was not aware till recently how fragile this grid of ours really is. I recommend the book that I mentioned here, Shorting the Grid, by our neighbor Meredith Angwin from Vermont. It's quite revealing, and I recommend it to everybody. The result of forced installation of renewables with production tax credits and curtailments and all sorts of incentives has so warped the grid that it has forced baseload plants, both coal and nuclear, out of business, and results in a more fragile grid. Careful analysis of wind and solar in terms of penetration of the grid shows that their value declines steeply as they penetrate. And that's because they really are inferior sources of power. They are irregular, they are harvesting sources of very low energy density, and their real utility is to supply a little extra when they need it. They are not suited to enter in a big way into the grid supply. And because of all these artificial supports I just mentioned, the only reason to build these things in many cases is because of the artificial supports. In fact, you see a quote there from Warren Buffett. Subsidies are the only reason to build wind farms. This shows something called the California ISO duct, kind of a funny term. It's based on the shape of the graph. Going from top to bottom, it shows the change in need for baseload power over the years from 2012 to 2020 as large-scale solar generation has been added to the California grid. And what you see is that you get excess energy from solar in the middle of the day. Sometimes they have to actually curtail it, but they still pay for it. Sometimes they have to pay to send it to Arizona and Nevada. And then when people come home at night to cook their meals and turn on the television and the sun goes down, they need to replace all of that excess irregular power with something else. The only something else that will work is natural gas. And as you see from the steepness of the neck of the duct there, that capacity has to come up really fast. And in order to spin up fast, it has to be already spinning, wasting energy. There in California, where this situation obtains, just as comparing Germany to France reveals about cost, the cost for electricity to California customers is going up much faster than in the rest of the country. Well, that's a quick overview of some of the deficits of renewables. I'll have a few more words to say, but just one little reminder first. The energy and pollution problem has to be solved on a global basis. If we solved it in this country, that would have little value if the rest of the world continued to use fossil fuels at a large scale. And because we use such an excess relative to our population, tweaking our consumption in America or Canada, for example, has very little relevance in the big picture. This is illustrated by this particular graph. It illustrates that if here in the US we reduced our consumption in half, which will never happen, and the rest of the world consumed electricity at that same level, we would need to more than double our energy production. We are not going to solve the world's energy problem by reducing the energy supply. That will never happen. Reducing fossil fuel pollution is important, but so is widespread world poverty, and alleviation of that poverty requires more energy. This is another illustration of that reality. Population on the horizontal axis, energy use on the vertical axis. The tall bar on the left is North America. So those of us in North America, a small fraction of the world population, use 1,500 watts per person. Europe, which with a similar standard of living, about half that. All the rest of the world is below that European standard. And notice that the last 3 blocks there, the very low bars, represent 10 times the North American population existing on 85 watts of electricity or less. In other words, 3 billion people on the planet subsist on electricity less than the use of your refrigerator. And 1 billion of those people have none at all. Well, when confronted with the deficit of irregularity, renewables proponents and enthusiasts will often speak about backup. We'll just use batteries. Well, this is a could-be scenario that is nowhere on the horizon. There is a lot of battery research going on right now, some of it looking at batteries that don't need rare lithium. But batteries are still systems of low energy density requiring a lot of material, a lot of mining, and all the rest of that. They have very short lives, relatively speaking. They degrade with time. They self-discharge. They don't solve the capacity factor. Batteries don't generate power. They only store it at some loss of power. And of course, there's a time scale problem with them. You can't save summer sun in a battery for the winter. This shows the largest battery storage center in California. It would take 15,000 of these and $750 billion to get 4 hours of backup for the United States electric grid, whereas our existing old-fashioned grid has 1.5 times overcapacity of dispatchable power at all times without storage. There are other forms of storage that people talk about. Pumped hydro is a pretty good one if you happen to have the right geography, and that's somewhat rare. There's molten salt, there's phase change materials, there's all kinds of ways that we could store energy. But you have to remember that whatever you pick, you have two losses. You lose energy when you go into storage, and you lose energy coming back out of storage. And you're lucky to get 80% of the original round trip. By contrast, with fuels, whether it's old-fashioned coal or uranium, the energy is already stored. You can use it on demand when needed. So, that was a quick tour through renewables and the reality of renewables. And what we come to see is that renewables have to contribute. They can contribute to the energy mix, especially to supply some of the excess needs that we have at certain times of the day. But they are not equipped to supply all of our energy. They are no way equipped to supply baseload power. It's just not in their DNA. Taking a quick look at the green sector of U.S. energy sources, you notice that nuclear is the largest one of those sectors. It supplies over 8% of our overall energy. It supplies 20% of our electricity. So let's now turn to nuclear and look at nuclear a little more closely. Nuclear has great potential. This is due to its enormous energy density. If you look at this comparison, any kind of chemical fuel, here from sugar to gasoline, 50 megajoules per kilogram or less, whereas uranium has millions. And this is because chemical fuels employ the relatively weak interaction of the external electrons of the atoms, whereas nuclear energy harvests the very high energy of the dense nucleus. To illustrate this more explicitly, that little fuel pellet is equivalent to a ton of coal. And in fact, if that were a pure fissile material, it would be equivalent to 20 tons of coal. But a pellet like that in one of today's reactors gives us the energy of a ton of coal. This is not something that we should reject because out of hand because we're afraid. Well, let's talk about what we're afraid of. The big fears are radiation, proliferation, and waste. And let's look at each of them. First, radiation. This pie chart shows worldwide exposure to radiation during your lifetime or during the world population lifetime. Notice that the majority of it, 82% of it, is coming from the environment. And you're getting it right now. You're getting it from the cosmic rays in the heavens and the radon in the ground. And you're having DNA damage in the cells of your body every second. But exquisite intracellular machinery has evolved to repair those breaks as they happen. And this does not really hurt us in any way. The remaining 18% of that radiation is almost entirely medical, diagnostic, and treatment. In this country, the proportions are different. We have so much radiomedicine that almost half of our exposure is from medicine. But there is a very tiny amount that you could ever get from the nuclear industry. We live in a sea of radiation. And in fact, if you have treatment for a cancer with radiation, you will get many orders of magnitude, thousands of times more exposure to radiation without harming you than you would ever get by being near some kind of a nuclear facility. Okay, but then what about accidents? That's the next place that we are concerned about radiation. There have been different incidents over the years, and some of them within the military a little more serious than within commercial power generation sector. But over all that long period of nuclear development, almost 70 years, there have been only 3 accidents in nuclear power plants, commercial nuclear power plants, at decreasing frequency over that period of time. These accidents have been thoroughly studied by the United Nations and the World Health Organization. And what is revealed by that study is that 2 of the accidents, 3 Mile Island and Fukushima, will result in no radiologic health effects or fatalities to the population that's anywhere nearby. In the case of 3 Mile Island, the very slight release of inert gases that they had to do at one point during the crisis was so slight that if you'd been standing right next to it, you would have gotten the equivalent radiation of a chest X-ray. Fukushima was a little more serious because they lost some of their containment and some radiologic materials were scattered around the countryside, but the concentrations are very low and declining quickly because of half-life. The one exception is Chernobyl. This was a terrible accident, about as bad an accident as you can imagine from a nuclear power plant. There were 2 explosions. Even the experts disagree on what the second one might have been, but we have in all cases the possibility of hydrogen explosions and steam explosions. We probably had both in the case of Chernobyl. Well, in the immediate aftermath of this accident, there were actually less, but about 50 deaths. And those were from the workers who were right next to this thing, trying to put out the fire and deal with the accident directly. They perished from acute radiation syndrome. In fact, over 100 of their co-workers who contracted this excessive radiation syndrome survived, and some of them are living today. There were 15 more deaths recorded so far. There will be more, or more cases at least, of from thyroid cancer of folks who were children at the time of the accident. This could have been entirely avoided if the Soviets had responded correctly with food warnings and potassium iodide tablets. Fortunately, this is a treatable cancer, so the fatalities are not expected to rise very much above this over time. This is not to say that this is okay. It wasn't okay. It was a terrible accident. But it is to say that we have to realize what the real dangers are and not so overblow them that we enter into a land of irrational fear. So that has to do with the amount of radiation that was actually emitted by Chernobyl. The second thing to say about the Chernobyl accident is this: it doesn't really count as a summary indictment of the nuclear industry. This was a terrible design being recklessly managed with no containment structure. No one would ever consider building a nuclear power plant like this going into the future again. Fear is the big killer, not radiation. Well, the second of the big fears is proliferation. In the wake of 9/11, we've all gone a little crazy about the imaginative ways that terrorists might affect us. And we come up with all kinds of wild scenarios. Well, stealing nuclear fuel or spent fuel from a nuclear power plant, a heavily guarded nuclear power plant, borders on the ridiculous. And even if you did, which you couldn't do without heavy equipment, the material that you would steal would be useless from a proliferation standpoint. Weapons-grade uranium has to be made in centrifuges, and it has to be enriched to a very high level. You couldn't use the fuel because it's already been turned into an oxide, and you wouldn't use the spent fuel because it's full of radioactive fission products. The plutonium that's produced in these reactors is also unsuitable for weapons because of the mixture of plutonium isotopes. This was discovered during the Manhattan Project. Reactor fuel is in an insoluble form, as I mentioned. The waste is heavily guarded, and the dry cask storage is extremely secure. The third big fear is waste. In fact, this fear of waste is almost completely upside down. Waste is actually a feature of nuclear, because nuclear is the only power generation technology that contains all of its afterproduct, and the volume is very small. No one has ever been harmed by spent fuel at a nuclear power plant. You will hear the discussion of thousands of years or millions of years that we need to store this material. Well, that's an extreme exaggeration because only 1% of the spent nuclear fuel consists of that plutonium that is so fearful because of its 24,000-year half-life. We do know how to deal with material like this. The U.S. military is already dealing with a pilot plant in New Mexico where they bury it a half a mile underground. This has been studied extensively by engineers and scientists throughout the world, and many of these deep geological storage facilities are being built and planned. But there's another option. If we, again, reprocess the fuel, you don't even have to bury that plutonium. You can put it back into reactors as fuel. What we take out of a conventional water-cooled reactor is only 5% used from the energy availability standpoint. Meanwhile, we allow all kinds of dangerous chemicals to run around our roads and fields and railroads with minimal protection. Ammonia, hydrochloric acid, various chemicals that if you had an accident, they would be far worse than even a dirty bomb. In fact, there are no technical obstacles to safe storage of spent nuclear fuel. I'll repeat that. There are no technical obstacles to safe storage of spent nuclear fuel. The only obstacle is public acceptance. These are the dry casks that I mentioned. Dry cask storage. This is similar to what you have after closing a plant like a Pilgrim. What we do with conventional reactors is take the fuel rods out at a certain point when we have to for technical reasons. We put them in a 40-foot deep pool of water for 5 years where they lose 95% of their radioactivity. After that, we can take them out and put them into these rugged casks. You can see that you can walk right up to them. There's no danger at all. And when I say rugged, they're really rugged. They've been tested for penetration, fire, flood, everything you can imagine, running into them with locomotives. These are very safe and secure right where they are. There is one other fear that I didn't originally list, and I'll just address it quickly. The cube in the middle represents natural uranium as it comes from the ground. It has two principal isotopes, uranium-238 and uranium-235. The uranium-235 is what we need for power plants or for bombs. But it is only 0.7% of what comes out of the ground. It's those 7 out of 1,000 yellow balls that you see there. Now that's not easy to separate because all of the balls are the same chemically. So today we use centrifuges. There have been other methods that have been employed. So that natural uranium is 0.7%. If we want to have a water-cooled conventional reactor, we have to get up above 3%. So we enrich the fuel. And you can see the cylinders there that represent natural and then power plant fuel. The bottom one is a nuclear weapon. You have to enrich to above 80% before you can get a nuclear weapon. So the fear that a power plant can explode like a nuclear weapon is absurd. It's physically impossible. Just make one note that the CANDU reactors that the Canadians have designed and employed can run on natural uranium without enrichment. I've mentioned these water-cooled reactors, which is what we have today. These are our legacy reactors. There are about 440 of them in the world, supplying about 400 gigawatts of power to the grids around the world. As I've tried to emphasize, these reactors are in fact safe, well-designed, and they are providing an essential green supply of energy. But there's something more to share about all this. In the near future, there are some big improvements coming, some more developments to add to the suite of available tools. One of the things that many developers are working on are what we call small modular reactors. You may have heard them referred to as SMRs. The idea behind small modular reactors is that you will build them in series production in a factory, take them to a site on a truck, put them in the ground, and turn them on. I'm oversimplifying, of course, but this is in contrast to spending 10 years building an enormous, thick, heavily reinforced concrete structure and all of the rest that goes into a conventional nuclear power plant. A subset of the small modular reactors that's very interesting is the molten salt reactor, and a subset of that is the thorium fueled molten salt reactor. Some of you may have heard of thorium before. Molten salt reactors are simple, they can't explode, they can't melt down, they're walk-away safe. And we did it already. We did it for 5 years in our Oak Ridge laboratories. What you see on the left are a couple of technicians putting together graphite logs that will serve as the moderator. They get put into that can on the right, which gets put into a silo. You can see the circulating pump and heat exchanger if you look closely. A thick shielding lid is put on top of the silo, and then you run the reactor. Here you may recognize a couple of visitors to that reactor when it was running. The gentleman with the hat in the center there is Alvin Weinberg, a brilliant scientist who was the head of this effort. Al Gore Sr. is on his left. What is this reactor? Well, I mentioned molten salt. You melt a large volume of salt, fairly ordinary salts. One of them could even be table salt, depending on the design. And then you put a little bit of uranium or maybe a little bit of thorium salt in that mixture. It's melted. You circulate it around from the reactor vessel through a heat exchanger and back. It's often called a pot, a pipe, and a pump. It's a very simple reactor with wonderful features, and many companies are pursuing this, trying to bring it back to useful life. One of them is Thorcon. This is a U.S. company working with the government of Indonesia. Their brilliant idea is to make these barge-style reactor plants in a shipyard, then bring them to a location and put them in a special pier where they'll be served by a can ship, that slender vessel in the middle. And you can see in the red circle there's a can, which is the reactor. It's the reactor with a heat exchanger all in one little can, lifted out of the can ship, put into one of those little yellow trap door. It runs for 4 years without a tension, and then they turn it off and switch to the other side, let that one cool down, and then they swap them out using this can ship and go back to a central reprocessing and refueling facility. Power to the grid, right there from the barges. Another company that is very advanced in this effort is Terrestrial Energy in Canada, very strong company, excellent technology underway. And this is a similar case. You notice that in this case, within the red circle, you have, again, a factory manufactured reactor with heat exchanger brought in by truck. This is land-based, so it's brought in by truck, again placed in a silo. In this case, the reactor will run for 7 years before you turn it off, swap it to another one. When the first one cools down, you can either reprocess that salt or you can put it into long-term storage. It's a fairly elegant technology that's under pursuit by many today. There are others as well. I'll mention some of them. A quick contrast with what this small modular reactor effort has with conventional pressurized water reactors. If you look at this cross-section of a conventional reactor, notice that the glowing yellow and orange portion is the reactor. The structure around it is so enormous because in that reactor you have water pressurized to 160 atmospheres. If you do have some unforeseen accident where you lose that pressurized water, it will immediately go to a large volume of steam. That's why you need this rugged, huge building. And by the way, that yellow and orange portion there is not weak either. That's a forged steel container many inches thick. They're actually very safe. But continuing the contrast, on the left you see such a conventional reactor, many years of construction, a lot of material, it's all done on site, whereas a small modular reactor done in a factory can be delivered and put in below grade, occupying a much smaller volume. So I'm going to just quickly talk about the thorium version of a molten salt or other reactor, because it could also be used in other reactors, but it has a particular place in molten salt reactors. Uranium is element number 92. Thorium is its near neighbor, element number 90. Uranium, our ordinary fuel, is fissile. It can be split. Thorium is not fissile, but it's fertile, meaning that in an appropriate reactor, it will absorb neutrons, and by beta decay, as illustrated here in the picture, it will decay into a fissile isotope of uranium. It's actually a slightly different one than the one that we get from the ground. This is uranium-233, which is actually slightly better than U-235 as a fuel, slightly better. So now you have a breeding cycle, and you are making new fuel all the time from an element, thorium, that's 4 times as abundant as uranium in the Earth's crust, therefore hundreds of times more abundant than the U-235 that we enrich for conventional reactors. It has such potential that 6 kilogram ball in that hand there has equivalent energy to 230 train car loads of coal. Nevertheless, is nuclear something that is outdated, too dangerous, something that needs to be eliminated? That horse has left the barn. This is not going to happen. There are 50 reactors under construction in the world today, only 2 in our country, but they're being built and hundreds more on the drawing board. The Russians and Chinese are building them especially at an especially high clip, and the South Koreans are building them as well. In addition to those conventional reactors, those 50 reactors, the small modular reactors I just mentioned are being developed by numerous companies, something like 70 companies in 17 countries. Amongst the developments that are happening as a result of all this effort are floating reactors that the Russians are putting out. The Chinese are planning to do the same thing. The floating power plant that you see there is already in service on the Siberian coast of Russia, supplying both electrical power and district heating to the small community of Pevek. They're now launching a series of icebreakers. I think the third of this new series, they have older ones as well, has been put into service within the last month. These icebreakers maintain a year-round shipping lane along the Siberian coast of Russia, and they can break through 9 feet of ice. They're powered by the 2 small twin reactors. The Russians even have a nuclear-powered freighter that can carry smaller ships within it. This map shows what the Russians and Chinese are beginning to do worldwide, beyond their own borders. This is something to give serious thought to. Look at all the blue diamonds representing where the Russians are building power plants. The Chinese are already building in Pakistan, and they even might build one in Argentina. There was even some discussion of them building one in the UK. And what happens when they build these plants in other countries is that they gain decades, maybe a century of influence, because they will have the fuel supply and maintenance options that are all part of the deal, along with financing. There are, however, new efforts happening in our country. There has been some bipartisan movement in the last decade or so to re-energize nuclear research and development within our country. If you notice down in Georgia, the blue star represents the Vogtle reactors that will be coming online soon. You've probably all heard about these reactors. I'm going to talk about them again in a minute. But those are conventional Westinghouse AP1000 water-cooled reactors. The red stars represent new technology that is expected to be built in the near term. You may have heard of Bill Gates' Natrium reactor. They're down in the corner of Wyoming. This is going to be built at a decommissioned coal plant. And this is an excellent idea for our country. The DOE has already looked at this and identified up to 200 coal plant sites where we could easily put a nuclear reactor. It's a great site because you already have generating and generating facilities and connection to the grid ready to go. In Idaho, where we have developed over 50 reactors since the early days of the nuclear age, including the submarine reactor there in landlocked Idaho. You notice that I have 3 reactors listed, including the NuScale reactor. This is also a water-cooled reactor, but it's a small modular reactor, and it is the first reactor that has actually been licensed by the NRC with a design license. It's slated to provide power to utilities in the Northwest. Up in Washington, the XE100 pebble bed helium-cooled reactor will also be connected to the grid. And back down to Tennessee in Oak Ridge, there are actually plans for 2 or 3 reactors in the near term. Notice that there's one just up over the border in Canada. They've already broken ground to put in a GE Hitachi BWRX 300 reactor. The Canadians are very serious about deploying small modular reactors in several of their provinces. You notice that there are many reactors under development in North America, including many types: water-cooled, gas-cooled, salt and sodium-cooled, microreactors, something I haven't spent any time on, but you can make a really small reactor and put it up into a remote community in Alaska or northern Canada and supply power for 5 years with almost no maintenance and eliminate all that shipping and burning of diesel fuel. There's also a lot of development underway for more and more advanced fuel forms that are more rugged, provide more power per unit volume, et cetera, et cetera. There are all kinds of things. You notice that multi-lobe fuel. The one on the right, TRISO fuel, is very interesting. Many of the developers are using this. In this case, what you do is take fuel the size of a sand grain and surround it with a layer of an absorbent carbon and then a less absorbent carbon, and then you put all of that together, compact it, more absorbent layers and carbon layers, and on the outside you have carbide. So when you use these, either in a ball form or a cylindrical form, there's no way it can melt. No reactor has ever gotten near the melting temperature of silicon carbide. So you have a new, very safe fuel form that many of these new efforts are going to employ. So back to the Westinghouse AP1000. Now, many of you have heard or know about the development of these two reactors at this plant in Georgia, the Vogtle plant in Georgia. And this is the plant that is so often referred to in terms of excessive cost. The cost and time overrun has been enormous. It doesn't have to be that way. This situation happened because of insufficient original planning, Westinghouse going bankrupt, problems with the regulator, problems with financing. A whole host of things came together to delay the construction of an effective connection of this plant. These two reactors are shortly going to be connected to the grid. Now, in contrast to that situation, this exact same reactor design was meanwhile deployed, 4 of them, in China, on time and on budget, because they did not operate through this same mess that caused this problem here. Now, meanwhile, this reactor is what we call a Generation 3 Plus reactor, meaning it's had all kinds of passive safety added to it compared to Generation 3 reactors that have been built in the past. You notice the large water tank at the top of the reactor. This can drain passively in a controlled manner to cool the reactor in case of an unlikely accident without any kind of operator interaction. You would never get the situation again that you got at Fukushima, where they had the pumps below a too low seawall. That was an unforgivable situation. It wasn't even a problem with the reactor design. But in any case, passive safety is being added to these reactors. So with all of the different forms of nuclear generation that I've just discussed, including legacy reactors, advanced legacy reactors like this Westinghouse AP1000, small modular reactors, we have the capability of really making a difference in supplying green energy to the world. Well, while all of this development has been going on in various countries by scientists and engineers and researchers, public opinion has begun to shift. I say attention Massachusetts because I want to call your attention to what's in that red oval. In 3 years, support for nuclear amongst Democrats has gone from 37% to 60%. Now, in our blue Commonwealth, it's presently illegal to build a new nuclear plant. This is really ironic, because in our Commonwealth, with our world-class academic, high-tech industrial, and trained workforce capabilities, we could be leaders in the country, if not the world. This is something to think about. This is Dr. James Hansen. He was the first to really bring global warming to the attention of Congress back in 1988. He's also one of many very thoughtful scientists who know and have stated repeatedly that we really have to use nuclear if we're going to solve this problem. He also co-authored a study that you see mentioned there that pointed out that upwards of 2 million lives have been saved by nuclear so far in our country by replacing fossil fuels, particularly coal. So we return to where we began, energy realities. Pretty simple conclusions. Renewables can't do it all, and nuclear is a key to the solution. There are many books and resources that you can access for further education on these issues. Just pictorial view of a few from my library there. No math or physics required. A lot of excellent resources. I'm going to just mention a few here. In fact, you can go to the top listed site there, our site, econuclearsolutions.com, to see more resources. Those 4 bulleted resources are free online. Electrifying Our World, Roadmap to Nowhere are book length. Well, so is Without Hot Air. They're great resources. There are regular online feeds if you really want to get into it. I list 3 books there. Power to Save the World by Gwyneth Cravens is a great introduction. It's a few years old now. It doesn't even talk about small modular reactors. But here is a woman, a novelist, who protested against the building of a nuclear plant on Long Island when her children were young, and then had the opportunity to get educated about nuclear by a mutual friend. And her account of what she learned is full of detailed information and a very interesting personal history. If you want to just explore energy, big picture throughout history, Richard Rhodes' book called Energy is great. And Shorting the Grid, which I already mentioned by Meredith Angwin, is a great wake-up call about what we're facing right here in New England. I would like to close on a personal note. If you are a person who has been anti-nuclear for years or decades, you may find that what I shared with you today is more than a little jarring. Why should you take my word for it? Well, you shouldn't, of course, without further confirmation. And I urge you to find that confirmation, to do more research. A caution, you can very easily find a prominent expert who will support your former opinion. But guaranteed, there are many other prominent experts who will disagree. We actually have to do a little digging to get below the noise that surrounds us. We have to access the work of scientists and engineers and radiation specialists and all the rest of it. You have to sort through that, use a little logic, and then come to your own conclusions. I can only look you in the eye and say that what I've shared with you today is the result of hundreds of hours of honest research. I urge you to do a little research yourselves, because after all, in a democracy such as ours, you are the ultimate authority. Thank you for your attention.